Welcome to the lecture on electromagnetic fields and waves. Today's subjects are Faraday's law of electromagnetic induction, transformers, and Maxwell's equations. In 1831, Michael Faraday discovered experimentally that a current was induced in a conducting loop when magnetic flux linking the loop is changed. Here in the figure you can see a visualization of this experiment. The induced EMF and the change rate of flux linkage based on experimental observation is known as Faraday's law. That is, EMF is proportional to the rate of change of flux linkage, d lambda over dt. So we have mentioned that EMF is proportional to d lambda over dt. We try to write the EM equation for EMF. Closed loop integration of E dot dl is equal to the minus partial time derivative of B dot ds, which is the magnetic flux. We can write this equation with the derivative put inside the integration, which can be proven mathematically, to obtain the following equation, which is the Faraday's law of electromagnetic induction. Curl of E is equal to minus del B over del T. It is a fundamental postulate for electromagnetic induction. We have three different categories of electromagnetic induction. The first one, which is also called as transformer EMF, is the case when we have a stationary circuit in a time-varying magnetic field. The second category of electromagnetic induction is called as moving EMF, and it refers to a moving conductor in a static magnetic field. And finally, the third category of electromagnetic induction involves both a moving circuit and a time-varying magnetic field. It is a combination of the first two categories. For a stationary circuit with a counter C and surface S, we have a closed loop integration over counter C of E dot dl is equal to minus time derivative of surface integration of B dot ds. If we define EMF induced in a circuit with counter C as closed loop integration E dot dl and magnetic flux crossing surface S as phi surface integration of B dot ds, we can write down the equation for the induced EMF as V is equal to minus d phi over dt. This equation is known as Faraday's law of electromagnetic induction. So V is equal to minus d phi over dt. The electromotive force induced in a stationary closed circuit is equal to the negative rate of increase of the magnetic flux linking the circuit. The negative sign in the equation is an assertion that the induced EMF will cause a current to flow in the closed loop in such a direction as to oppose the change in the linking magnetic flux, which is known as Lenz's law. Finally, The EMF induced in a stationary loop caused by a time-varying magnetic field is a transformer EMF. What is the first thing that comes to mind when we mention transformers? Well, probably it's the cartoon character, but the subject of our lecture are these transformers. A typical transformer is depicted in the figure, where we have a primary and secondary circuits. A transformer is an alternating current or AC device. It's used for voltage, current, and impedance transformation. In general, it has a common ferromagnetic core to constrain the linking magnetic flux along a certain path. Basic equation for ideal transformer can be written in the following form: N1 times I1, where N1 is the number of turns in circuit 1 and N2 is the number of turns in the second circuit, with the current I2 is equal to Rv, where R here is reluctance. Reluctance is equal to lambda over mu s. Lambda is the length, S is the cross-sectional area, and mu is the permeability. We can write down this basic equation also in the following form, where we have the flux is equal to mu S over lambda is equal to Ny I1 minus N2 I2. In an ideal transformer case, mu goes to infinity. Thus, the basic equation takes the following form. Then, we can easily write down the following relation. First, the current. For the current, we can write down as I1 over I2 is equal to N2 over N1. For voltage, we have V1 over V2 is equal to N1 dV over dt over N2 dV over dt, which ideally is N1 over N2. For impedance, we have R1 EF is equal to V1 over I1, which in turn ends up in the equation of N1 over N2 squared RL. For the case of a real transformer with linkage flux, L12 is equal to L21 is equal to K times square root L1 times L2, where K is less than 1. K here is the coupling coefficient. For a real-life transformer, we have a finite permeability, we have a leakage flux, which makes K less than 1. We have non-zero winding resistance, resulting in limited Q factors and losses. We have nonlinear feature of ferromagnetic core, that is the hysteresis. And finally, we have eddy current losses, which generate additional heat loss. In order to reduce eddy currents, there are several ways to do that. One is using high mu and low sigma, that is high permeability and low conductivity materials. And the second is to use laminated cores, that is the ferromagnetic cores are coated. Here you can see two examples of laminated core usage in transformers in real life. Let's start the subject of Maxwell's equations. First, EMF, voltage, electric field, is induced by the change of magnetic field B. That is, curl of E is equal to minus del B over del T. And the second important equation is magnetic field intensity H is induced by the change of current I, or charges Q. This comes from the following two equations. The first is charge conservation, or the continuity equation, where divergence of J is equal to minus del rho over del T. Since divergence of D is equal to rho, and divergence of J plus del rho over del T is equal to 0, and we have curl of H is equal to J, using the identity equation, we can write down this expression. We have to modify curl of H with the charge conservation and modify this equation to take the following form, where we have the extra del D over del T term. It's called displacement current density. In this table, you see both the differential and integral form of Maxwell's equations. These four equations have specific names. The first one, either in integral or differential form, is called as Faraday's law of induction. The second equation is known as Ampere's circuit law. The third is the Gauss law, and the final equation refers to no isolated magnetic charge. The Maxwell's equations, together with the continuity equation and Lorentz force equation, constitutes the foundation of electromagnetics. This is the end of lecture 11. See you next time.